here's section 3 of our notes here on topic 8. Now we're going to look at wind power. And with wind power, we're looking at the rising air due to Earth's rotation, thus producing kinetic energy. So with that in mind, to be a little bit more specific, air heated by the sun becomes less dense, which causes it to rise. The combination of rising air and Earth's rotation produces wind. This wind then gives us kinetic energy, in which air is being used to run turbines to produce electricity. So what I have here is a picture at Bowling Green State University, and they're doing a lot of research with wind turbines. They're also working with places in Cleveland and near Toledo and over in Indiana as well, that they are trying to harness this wind energy. As I'm sure you're aware, Western Ohio is much flatter than Eastern Ohio, so wind power would be a good thing over in that area. Also, here's a look at Europe and its use of wind power in 2008. Wind power continued, looking at turbines. A turbine is like a fan or a blade on the propellers. So if we were to look at a picture of one of these, it would be this area right here. It moves due to the wind, not due to the wind moving because the blades are moving. The blades aren't circulating the wind. Sure, it has something to do with that, but how do the blades even start to get to move? That's because of the movement of the wind. So calculations, you've already seen one of these. Volume of the air passing by the turbine per second will then give you the mass of the cylinder of air, which then you can calculate the kinetic energy of this air, and also power eventually. So problems with the wind power, obviously a consistent windy place would be the best place, but the main problems are turbines are often built in areas of natural beauty. That's kind of sad because you would have to deconstruct some beautiful landscape in order to put those huge turbines up. Turbines are also not very reliable. What we mean by this is if there's no wind, then obviously no electricity will be generated that day. So you definitely want some wind. Currently, there are a lot of offshore wind farms, and this is an example of what a wind farm is. We're just talking about a lot of turbines that are placed together in Denmark. Denmark seems to be using them a ton. Let's move on to wave power. As waves spread out, so does their energy, which can be used to power turbines, which can be used then to produce electricity. Beneficial for wind power in isolated areas. So places that are kind of desolate would be a good candidate for wave power. Then that for the next slide just shows you what wind power looks like. So with that in mind, we'll look at water power here, and this says Palamus, which is a sea snake. Your bottom left picture shows you an example of water power. There's a total of 4 sections that have a complete length of roughly 150 meters. Each section is hinged so that the wave passes it, it bends. Okay, this bending drives pumps, turbines, which then flow power through electrical generators. What is generated is roughly 750 kilowatts. 750 kilowatts of electricity are generated. Sources not derived by the sun would be like tidal power. So let's try to harness any movement due to the tides. So tides are mainly caused by the rotation of the moon, right? Due to the difference in gravitational forces, we have high tide and low tide. This movement of water can be used to drive turbines, and then these driven turbines then produce electricity just by the idea of having high tide and low tide. That's pretty cool. Geothermal energy. How is heat generated? Friction. Okay, this is the big thing here. Friction between moving rocks and Earth's surface generate the heat. Geysers then occur, which happen due to water running into spaces between the rocks that create the steam because the rocks are sliding past each other, creating friction, thus an increase in temperature, form of non-mechanical energy. That steam is then harnessed. Okay, that steam is used to produce the electricity. Very expensive to start up, but it definitely saves you some money in the long run. Wood. Wood is possible, but it has only half the energy density as coal, so therefore you'd have to burn twice as much wood to get the same amount of work done that coal would get you. So a problem, all of that fuel, all that coal must be carried along with the steam engine when you're transporting it from part A to part B. Oil has a higher energy density than coal. Good to know. But it needed to be refined in order to be used. So a gentleman in 1852 came up with kerosene. Oh, wow, I misspelled that. Kerosene, E-N-E, is much cleaner and has a higher energy density than coal. It could be injected into a piston in an engine instead of heating it from the outside. Therefore, it's now called an internal combustion engine. A problem with using kerosene, though, although easily pumped from an oil well, an oil spill may occur. This oil spill may have negative effects on ecosystems. Obviously, that's not good. Faraday in 1831 invented moving a wire into a magnetic field, and then Siemens in 1866 invented dynamo, and electricity generation was produced on a larger scale. Pearson then in 1884 invented the steam turbine. So what about electricity now? Well, at this point in time, electricity was the easiest way to transfer energy from one place to another. Here is a picture that was taken back in those days on Siemens electrically driven engine. Huge. It's very, very large, so we can tell how things have downsized throughout the years. Obviously, that's a good thing. Coal-fired power stations. Now we're going to look at coal-fired, oil-fired, nuclear-fired power stations. Specifically coal-fired. Heat from a furnace boils water in the boiler that runs into steam, and then it powers the turbine, in which the turbine turns a generator that produces electricity. When steam comes out of the turbine, it is then cooled in a condenser. Once it condenses, this water is then returned to the boiler, and the system starts again. So this is very cyclic, okay? There is a cycle that can occur over and over and over again. That's pretty good, right? That's something that you would want, but obviously there's going to be some release of CO2 into the air, thus increasing greenhouse gases. Coal-fired power stations are about 40% efficient. Well, why? Not all chemical energy from the coal gets converted into electricity. Some of the things that are converted then are going to be exhaust heat. That didn't come out right. Some of the things that are going to now be present due to this non-100% conversion, thus making it only 40% efficient, is now we have exhaust heat, waste heat, and friction. So once again, here's a nice Sankey diagram. So you would start off with 100 units of energy stored in the fuel. So this is like everything at this area. And then, which means, okay, so you can see how everything chunks off. And once again, the wider, the more energy. The thinner, the less energy. Oil-fired power stations. Similar to coal-fired, but oil is burned to produce energy, which is needed to boil the water. Benefits, though, while oil-fired is cleaner than coal, it is cleaner than coal, and it is easier to drill and extract from the ground, thus making it easier to transport. Gas-fired power stations, i.e. natural gas, is more efficient than coal because there can be two stages of energy use. Burning gas is blasted through a turbine when the heat produced by the burning can be used to boil the water, and then that powers the steam turbine. Their efficiency is at 59%. So over here, we saw that coal-fired was at 40%. Now we're making progress because we're at 59%. Well, if the wasted heat is used to heat houses, then it's about 80% efficient. So if you can find a way to harness all that quote-unquote wasted heat, your efficiency definitely jumps up. Here's a great Sankey diagram for you to take a second and just look at, guys. Okay, I would totally make sure that I understand these Sankey diagrams. Please make sure you look at them. Here's an example of a gas-fired power station in the UK. Okay, nuclear fuel. Uranium is what we need to look at here, and it's taken out of the ground as uranium ore, and it's processed into a metal that is more than 1.5 times denser than lead. Lead's pretty dense, guys. It's made up of several different isotopes, most commonly uranium-238. About 99.3% of it is going to be uranium-238, the nuclear fuel. Does a chain reaction occur? No, but fusion does occur. But there's no fusion, so that's why a chain reaction does not occur. So enrichment. It is done to be used as a nuclear fuel. It is made into small cylinders that are stacked together to make the rods. These rods are then bundled together to called a fuel bundle. These fuel bundles are now stored in nuclear reactors in the nuclear plant, obviously. If there's more than one neutron that's present, then fission does occur, which does accelerate a reaction. So what they have done here, so that the reaction does not get out of control, if there's like tons and tons and tons of fission occurring, splitting of unstable nuclei, they have created something called insertion. And insertion is when a neutron-absorbing material is placed between fuel rods. That neutron-absorbing material is boron rods. These boron rods will then control the rate of the reaction. Well, what if something goes wrong? It's kind of like an atomic bomb dropping. And this loss of control could be something as small as a soda can. Therefore, that means that a chain reaction, fission, will just go out of control. In a nuclear power station, energy is released when the nuclei split. This splitting of nuclei, you know it as fission, but it's called fission fragments. Due to this, there is an increase in temperature. So, nuclear reactors produce heat, and they contain fuel rods that are surrounded by graphite. Now, what about these control rods? The point of them is to raise or lower the rate of reaction. So control rods literally control the rate of the reaction. They are housed in pressure vessels in which a gas is circulated to pick up the heat from the fuel rods that is transferred to water in the heat exchanger. This water then turns into steam, which then turns the turbine. Then that water is cooled in the condenser, and the process begins again and again and again. Here's some nuclear power plants that are in the United States. We have some in Ohio, as you can tell. And here is a picture of what the inside of a nuclear power plant would look like, all the different parts and pieces to it. Problems with nuclear energy. Extraction of the uranium is definitely a problem. There's mining that's definitely causing to some devastation. There is an alternative to mining. It's called leaching. But this leaching may contaminate the groundwater, which is then obviously not good for the people that are living near these nuclear power stations. Also, another problem with nuclear energy is radioactive waste that are left behind. These are called tailings. Something else that might be a problem is if the nuclear power plant goes into meltdown. Well, meltdown is literally when the fuel rods melt. When the fuel rods melt, that means that radioactive material is now released into the atmosphere. Well, how could this happen? Why would this happen? There may be cracks in the pressure vessel, or there may be a malfunction with the cooling system. I'm not sure how many of you are aware of this, but not too close, but also not too far away, over in Pennsylvania, 3 Mile Island, there was a nuclear meltdown. The left-hand picture was prior to the meltdown. The right-hand picture was after the meltdown on what it looked like. Yikes. Okay, nuclear power wastes. Low-level waste. There's old reactors and process fuel enrichment and transfer the heat from the fuel rods. There's high level of waste. This would be disposal of spent fuel rods. A spent fuel rod has a half-life of about 1,000 years. So it takes many, many, many years for them to be depleted. Making weapons from fuel? You cannot use these spent fuel rods to make the atomic bombs, but you can use them to make atomic weapons by reprocessing the spent fuel rods, because the spent fuel rods have now gone through the chain reaction of turning uranium into plutonium. They can use the plutonium for the weapons. Benefits of fission, though. CO2 production? There is none. So therefore, there's no greenhouse gas emissions going on with nuclear power plants. That's pretty darn good. Sustainability. Uranium might not be everlasting, but fission produces plutonium, which can also be used in a nuclear reaction. So you could maybe then start your power plants in which plutonium is going to be your lead off instead of the uranium. Well, we've been talking about greenhouse effects, so let's look at greenhouse effect here. It's the warming of a planet due to its atmosphere, allowing in ultraviolet radiation, but trapping infrared radiation that is emitted from the warm Earth. So think about these two questions. How does the energy from the sun get to Earth? And what is the interaction between the energy and the atmosphere on Earth? You need to answer those two questions, okay? Kind of research that a little bit. I give you a nice little diagram over here. This ends our third section of topic 8.